Hello everyone, I hope you are doing well. In this video, we are going to solve a problem related to variational method. Okay, this is the example problem. Before the video, we have seen that what is the variational method, and now we are going to use that method in finding out the energy states and wave functions for a 1D harmonic oscillator. Okay, so this is the example problem from quantum mechanics by Zetley, and let's see the problem statement and then we'll dive into the solution directly. The statement says consider a one-dimensional harmonic oscillator. So here we are considering a 1D case of harmonic oscillator. Use the variational method to estimate the energies of the ground state, the first excited state and the second excited state. So in this problem, what we are going to do is that we'll consider a one-dimensional harmonic oscillator. We'll write its Hamiltonian, and after that we'll use variational method specifically to estimate the energies of its ground state, the first excited state and the second excited state. And besides that, we'll also estimate their wave functions for the ground state, for the first excited state and for the second excited state, because once we know the energies we can easily determine the wave functions as well. It's not difficult, so we'll do that thing in this video as well. Let's quickly get started. We just moving towards the solution. As we can see here, the whole situation for a one-dimensional harmonic oscillator. Let us first write the Hamiltonian of our system, because that is something that we'll be using later on. So the Hamiltonian is given by, Hamiltonian actually represents the operator for energy, and we know that any system that we have on earth or in universe has two types of energies: kinetic energy and potential energy. The Hamiltonian is given by, this is Hamiltonian, and it is equals to kinetic energy, which in terms of quantum operators it is equals to minus h square by 2m d square by dx square. Okay, in terms of operator, this is the kinetic energy operator, and plus we have, this is actually del square in 1D. Okay, so we can also replace it by this thing, but in 1D, that is why I just inserted this value right here. We use the total derivative because in 1D there is only one variable and hence it is x. So d square by dx square, and potential energy, which is 1 over 2, it is normally 1 over 2 kx square, that we know k is equals to m omega square. So I'm gonna put m in place of k, so it's 1 over 2 m omega square x square. Okay, this is the usual term that we already know in classical physics as well. We normally use that expression for the potential energy of harmonic oscillators. So this is a familiar term. We can put the value of k right here, which is m omega square, that we also know from classical physics. So it becomes 1 over 2 m omega square x square, m omega square x square. X is the operator here. Here this is the operator, and here x is the, x squared is the operator, because we are considering here the Hamiltonian operator. That is why all of the things that we have wrote here are operators. Okay, so I have also mentioned the alternative forms that are really familiar to us, so you can relate with what we are writing here on the basis of the familiar terms. So this is a Hamiltonian. Let us call it as 1. Now in variational method, now let's estimate the energies of ground state, energy of ground state, energy, you can say, of ground state using variational method, Okay, so we'll give that heading of ground state calculation using variational method. It could be a heading so that we may know that we are focusing on this state for now, then we'll do it for first excited state and then for the second excited state. In variational method, there is only 2 to 3 to 4 major steps that are always replicated again and again. So let me tell you those steps so that it may become easier for you to imagine what's going to happen next. First of all, what we do is to suggest a trial function for the state, trial wave function, you can say trial wave function for the ground state, for example, because we are now calculating it for the ground state, so we'll suggest a trial function for ground state. If we are doing it for first excited state, then we'll suggest a trial function for the first excited state, and so on. Okay, depending upon which state you are considering, you will devise a trial wave function for that state. So we'll first do it for the ground state. We'll suggest a trial function, then we'll calculate the expectation energy. Okay, its formula we know that is equals to that trial function, Hamiltonian trial function. Okay, and since we are we'll consider a wave function that is normalized, that is why we are not writing this thing in the denominator, because by normalization we already assume that this is equals to 1, and it is adjusted by the normalization constant that we'll introduce in trial function to make sure that it is a normalized wave function. So this thing doesn't needs to be written, and we'll calculate this. Second step is to calculate this thing. Okay, after calculating this thing, we'll differentiate it with respect to the adjusting or the compensating parameter that we have introduced in the trial wave function for the things that we are not sure about. Okay, we'll see in an example. We'll differentiate it, and that differentiation would be made equal to 0, and we'll find out the value of those parameters. For example, it's alpha, so we'll calculate the value of alpha. We'll put that value of alpha into trial wave function that we suggested, and then into this energy expression that we got, and we'll get the energy values as a result. So this is it. The process is really easy. First is to devise a trial function, second is to find out the expectation energy using the Hamiltonian of the system you have, and then we'll solve it, and then we'll take its derivative with respect to the unknown parameters, and we'll put it equal to 0, and we'll find out those unknown parameters, and after finding out those unknown parameters, we'll put them into this energy expression to get the energy that we are interested in, and put into this trial wave function to get the associated wave function for that state. Okay, that is it. The process is same even if you're finding out the first excited state energy, second excited state energy, or whatever it is. The process will remain the same. We'll devise a trial function, we'll find out expectation energy, we'll derivate it equal to 0, find out the unknown parameters, and put them back into this equation to get the energies and wave functions. That is it. That is the process basically. So let's do that using variational method ground state energy. So for ground state, here we have that benefit about harmonic oscillators, that we already know their original solutions. We know what their exact solutions are and how the how system looks like or what are its properties. That is why we can make a very good guess about the trial, about the wave function, about the expected wave function for the ground state. Okay, so we'll use that prerequisite knowledge about harmonic oscillators into this problem, because since we already know the situation, so we should take benefit of that thing or that fact that we already know its solutions. So that is something that we'll be doing here as well. For ground state, the wave function should be the trial wave function that we are considering should be even, which means it should be symmetric about origin. Okay, it should be symmetric and it should be even, and besides that it shouldn't have any node. Since it's a ground state doesn't have any node in harmonic oscillator. It shouldn't have any node. By node we mean that the wave function should not be equal to 0 anywhere except at infinity. Okay, except at infinity it shouldn't be 0. It shouldn't be 0 anywhere. If it is 0 somewhere, that point is considered as node. Okay, node and antinodes, you already know what they mean. Antinode, we used to have its definition in normal physics, like antinode is a point of maximum displacement from mean position, and node is the point of zero displacement from mean position, which means um, 0, wave function is 0. Here in quantum mechanics, by node we means the wave function becomes 0 at node, which means destructive interference. Similar concept, it's a really similar concept to what we used to have in classical physics as well. So it shouldn't have any node, and it should be well-behaved wave function. Well-behaved wave functions, because well-behaved wave functions gives us some beneficial information, and that is why it should be well behaved, and for that purpose it should approach to infinity. Oh sorry, the wave function, as x approaches to infinity plus minus infinity, the wave function should approach 0. Okay, it means that the psi that we are gonna suggest here should approach 0 as x approaches plus minus infinity. These are the some conditions that we are imposing on our ground state wave function. It should be even and symmetric. By even, it ensures that it is 0 for both plus infinity and minus infinity. That is also a benefit of using an even function for the ground state. With the situation that it shouldn't have any node, it means it shouldn't be 0 anywhere else except at plus minus infinities. These are all the conditions that we have for the ground state wave function. Now let's write a ground state wave function, and we are really familiar with this form. Let's write it as ae minus bx square. Here b is the adjustable parameter that is to be calculated later in the video, and it's a part of the variational method. Okay, in variational method we introduce some adjustable parameters that would be calculated later on to accommodate the things that we couldn't guess about the wave function. Many books uses alpha as the adjustable parameter. Okay, but I'm using here b. The reason is that when I was solving this problem by myself, using the alpha sign normally got me tricked with some other symbols, like I mixed it with a or 2 or something like that. That is why I used b here to make it easily be seen and differentiated from rest of the parameters that we have in the equation. So it's just a representation, just a symbol, just a arbitrary symbol, I would say. And it doesn't matter if you take alpha, beta, b, c, or whatever you are taking. It depends upon your convenience and what you see as visually appealing. So that is the reason I used. You can obviously use alpha right here, it's totally up to you. I'm using b here. If you already know what are the solutions of harmonic oscillator, you can see that this function is really a crucial part in harmonic oscillator solution, and that's why we are using it here. And if you see if this wave function satisfies these conditions or not, you can see it's an even function, because if you put plus x or minus x here, it will remain the same. The function will remain the same on in both the cases. At the end of this video, maybe I'll justify like it's satisfying these conditions, because sometimes students just get annoyed by the length of the video, but I just want to assure it that you are getting your answers and justifications. If you put this wave function equals to 0 if you want it to be equal to 0 to see if it has any node or not. So you can see here we have this situation equal to 0. Psi is actually this now. So a is a normalization constant, it can't be equal to 0, so only this thing is left. And if you put this thing can only be equal to 0 if x is equals to plus minus infinity, it can't be equal to 0 otherwise. The exponential function is never 0 for any other values except infinities. Okay, so only infinities can make a exponential function equal to 0 when it has some appropriate sign. Okay, like it should be like that, it should be e to the power minus infinity to make it equal to 0, otherwise it can't be. So that only happens when x is equals to plus minus infinity, and this function is never equal to 0 anywhere else. So this is how the condition of no node is satisfied. It is an even function. For example, if e to the power minus bx square, if I replace it by minus x whole square, so it becomes minus b minus x whole square is x square recently. So we have e to the power minus bx square again. For the positive value of x and for the negative value of x, we get the same psi again, so it means it's a symmetric function or a even function. So all of these conditions are satisfied at x to the x. As x approaches positive infinity, it becomes infinity square, which is again infinity, so it's e to the power minus infinity, which is equals to 0. And if we use e to the power minus infinity like here squared, so it will become e to the power minus b plus infinity. Okay, and e to the power minus infinity, again the same situation, as b multiplies with the infinity to become infinity again, so we have negative infinity, and this is equals to 0 again. So we can see here that it is satisfying all of these conditions. It is becoming 0 at both x plus as x approaches to plus infinity and minus infinity. So yes, this is the perfect wave function that we can have for the ground state of the harmonic oscillator, and that's what we are gonna use now. A is the normalization constant. We can determine it right away so that we can put its value at the end. Okay, so first of all, let us calculate its normalization constant, because this is a part of the video. We have to determine it. We can determine it using this thing. Normalization condition is that in terms of ket-bra we write it like that. This is normalization condition, that this scalar product should be equals to 1. In ket-bra notation we write it like that, that should be equals to 1. And this is something that we had in the denominator as well, as you have seen it, where as I wrote it here, the denominator equals to 1. This is actually the normalization condition. And if we expand it in terms of integral, it means integral is our whole space, it's our whole space. Then this is the psi in bra notation, which means it has complex conjugate over it, and this in ket notation is simply the same. And derivative will be on whole space. Since it's a 1D, so it will only include dx. Otherwise, if it would have been 3D, then we'll be using dx, dy and dz, or simply dv, which is volume differential volume. So since it's 1D, so we'll use dx only, that should be equals to 1. Now let's put the value of psi right here. We can see there is no iota here, that is why psi star and psi simple, they will be equal to each other. If there would have been any iota right there, then the situation could have been different, like conjugate becomes different. But in case of terms which are not imaginary, the conjugate is equals to the simple wave function. So let us put in here, in place of psi star we'll write a e to the power minus bx square. Then we have psi again, so we'll put psi again, bx square dx equals to 1. We can see here it remains the same because there was no iota. If there would have been iota, then we had to change iota by minus iota. Okay, that is how conjugate works. Star means taking conjugate of that wave function. So this a and a becomes a square, and since it's a constant, will come out of the integral, and we have integral minus infinity to infinity e to the power minus bx square, and it's minus bx square, one more exponential equals to 1. Now when bases are same, powers gets added. Okay, when we have same bases, we can see here we have same bases here, e and e, so powers could be added under the same base. So we simply wrote its power with the similar base since they were both same, so it becomes e to the power minus 2b x square. It's 1bx square minus 1bx square, so it becomes minus 2bx square dx equals 1. Now what is the value of this integral? If we know its value, then we can determine the value of a. Now let me tell you its value. Since the integral e to the power minus the integral from limit minus infinity to infinity e to the power minus ax square, I'm writing here the general formula. We can put the value of a to be 2b here, so our case is there. So it is equals to under root of pi by a. Pi is always there, divided by the thing that comes with x square, which is a here. Okay, and in our case we can see, so in our case we can see we had e to the power minus 2b x square, so it means we'll replace a by 2b and we'll get a value. Okay, here the value of a we can compare. Here x square, here is x square, here is negative, here is negative. A is here and it's 2b here, so it means by replacing 2b by a we can simply get a value, so it is under root pi by 2b. Okay, let's put this expression where? In 3. Oh, why I wrote it again? So this is expression number 3. Put it here, this value. A square equals to, taking it here, so it is inverted. It's here in this side, we took it here to take the value of a, and it's a square equals, we can write it as 2b by pi whole power 1 by 2. Under root is equivalently this, so we need to take under root on both sides, the power 1 by 2, the power 1 by 2 on both sides to get the value of a. So it's 1 by 2 already, so 1 by 2, one more, because of this it was 1 by 2 already. Taking 1 by 2 again means we are multiplying it on both sides, so this is cancelled and it's a in here, and this is 1 by 4 in this side, so it means a equals 2b by pi power 1 by 4, 2b by pi whole power 1 by 4. This is the value of a. It is the normalization constant and we have to remember it. Now let's continue with the psi function that we had, and we'll not put its value right now because we'll put it at the end of the problem. Okay, when all of the things are simplified, and we had psi equals a. It's, since it's ground state, I'm using 0 here. Okay, a e to the power minus b x squared. Now we know the value of a here, so now the expectation energy, the ground state, the expectation energy is given by for ground state, so we'll use E naught here. Okay, let us open it. So it's this psi naught static because it's in bra vector, so it will be static. Then we have h, then sine out again, and dx, since it's 1D. Now next step is to put the value of each of these things right into this expression. We left at this point. Now let's put the values of wave functions in Hamiltonian here, and we have this thing for psi naught star, and in place of Hamiltonian we'll put the value of Hamiltonian that we know. Alright, plus 1/2 m omega square x square. Okay, and lastly we'll put the value of psi naught here. The order matters here. Okay, you can't write psi naught just before Hamiltonian. You can't interchange their positions. Okay, here order matters. Hamiltonian will only act on this wave function. It will not act on the one whose conjugate was calculated. Okay, it is before the Hamiltonian, so Hamiltonian will only apply on psi naught. So we'll write it at the right side of Hamiltonian, bx squared and dx as it is. Okay, this a and a becomes a squared, and we can write them outside of the integral. Then we have this thing, and I'm letting here minus h squared by 2m as equals to c. I'll put its value right at the end just to avoid any complications, because this is something that we have to write again and again in every step, and it makes it look messed up, like there is so many things being written here. So that is why I just let c to be equals to this, and we'll put it at the end. And then we have e to the power minus b x squared dx. Now it's the time to actually multiply it inside this thing, because it's actually the operators that has to be applied on this wave function. D squared dx squared e to the power minus bx squared. Okay, it will appear on the right side of each of these operators. In case of operators, you have to be careful where you are writing them. So the operator is on the left hand side, so it will appear on the left hand side, and this is, since it's in the right hand side, so you will write it on the right hand side of these operators. And dx here, dx is here. And next, let me write it in a clear form so that e to the power minus bx squared plus 1/2 m omega square x squared e to the power minus bx squared dx. Now in case of position operator, what happens is the function on which it is applied remains unchanged. Okay, the position operator works in this way, like if x applies on psi, it is equals to x times psi. Okay, similarly, if square root of it is applied, so the function as a whole remains the same. That is why I just replaced x hat square with simply x square. Now let me calculate this thing separately, and we'll put it right into this expression. Okay, that would be better. So d square by dx squared into e to the power minus bx squared. When a lengthy calculation is a part of a lengthy thing, so it's better to calculate it separately and put it right back into the equation. So let's evaluate it. It's a double derivative, so we'll first apply single derivative and write this expression like that. Since it's a double derivative, so we can write them d by dx into d by dx of this. We'll apply first derivative, then we'll take another derivative of it. Derivative of exponential works like that. We have the exponential term as it is, then we take the derivative of its power. So we have d by dx e to the power minus bx squared minus b is constant, so it will come out of the derivative, so it's only applied on x squared. D by dx e to the power minus bx squared minus b, derivative of x squared is 2x. Next is 2b and negative, this is constant, so I'm taking it outside, and the d by dx will be applied on x e to the power minus bx squared. Since there are two terms, so we'll apply the product rule on it. X as it is, derivative of second term, this is first term and this is second term, we can divide them like that. So first term as it is, derivative of second term, then second term as it is, derivative of first term. This is how the product rule works. And x dot derivative of exponential again, so it's equals to e to the power minus bx square dot derivative of its power, derivative of its power is minus 2bx as we calculated before, and that is why I'm writing it directly. Dx by dx is 1, so it's e to the power minus bx square only here, minus 2b into, this is a negative sign here, 2bx square e to the power minus bx square plus e to the power minus bx squared, and yes, this is the to the power minus bx square, and this is what we have got so far, and I think it's a good form to insert into the expression. So let's put it back into the equation that we were solving. Here it is, we will put this value of this double derivative of e to the power minus bx squared, this term right here, in place of it we'll put this value. Okay, let us do that now. Let me write here the expectation value for the ground state energy equals a squared minus infinity to plus infinity e to the power minus bx squared, then we have this bigger bracket, that bigger bracket, and then comes c, and now I'm gonna write the value of this double derivative right here, which is minus 2b into, okay, minus 2b, it is being multiplied by the whole quantity, so another bracket starts, and we have minus 2b x square e to the power minus bx square plus e to the power minus bx square. Okay, we have inserted its value now, plus we have this term plus 1/2 m omega square x square e to the power minus bx squared, and the bracket, bigger bracket closes, we have dx now. What else can happen now is that we'll multiply e to the power minus bx square with these two quantities, okay, so that we may get a simplified form that could make some sense. Then after multiplying it, we'll also separate this integral sign with each of these values. Okay, we'll write this thing with this expression as well as with this expression. For simplification, it will become minus 2bc. Okay, here minus 2bc, and we have this quantity whole here. We have to separate and simplify all of the integrations in order to insert the values of integration at the end. So before that, we have to convert it into a simplified form, and a square, this term is common to both of these quantities, that is why I'm writing here again, and then we have this quantity which is 1/2 m omega square x square e to the power minus bx square, and oh, it's dx here as well because we have separated the integrals, so dx will appear here and here as well separately. And let's simplify it further on. We have minus 2bc, which is a constant quantity, so it will come out of the integral, and let me write equal here, and it's negative now. 2bc is out of the integral now, and e to the power, now let's multiply e to the power minus bx square with both of these quantities inside, and we will get minus 2b, this minus 2b x squared e to the power, it's minus bx square, and this one also, they both multiply to become e to the power minus 2b x square, as you already know. So plus sign, then it multiplies with this quantity, it becomes minus 2bx squared, becomes, because there are two of these being multiplied, so the power adds with the basis being same, and it's dx here, plus a square. Now taking the constants outside of the integral, m omega square is a constant, divided by 2, so it's e to the power minus infinity to plus infinity x square first, then e to the power minus bx square, and it's e to the power minus bx square, two of them, so it's e to the power minus 2bx square dx. Now let's separate this integral on both of these quantities as well, because we want to make it in simplified form as possible. So this thing is being multiplied by both of these quantities, so it will appear for both of these quantities. It's e to the power minus infinity, limit of integration from minus infinity to plus infinity, then we have minus 2b x squared e to the power minus 2b x squared, then minus sign, this one a square, 2bc here again for this one quantity, it's dx here as well, it's dx here as well, because we have separated the integrals, please consider it. It's okay, we have successfully separated the integral on both, and what we'll do next is to take out all of the constants from the integrands and take them out of the integral, so that we may replace their values from the well-known results about the integrations of these integrals. It's minus 2b, which is constant, so minus and minus becomes plus, 2 and 2 becomes 4, b squared a square c, and then we have e to the power minus, oh why I see this, it's limit of integration from minus infinity to plus infinity x square e to the power minus 2b x square dx, then we have minus a square 2b capital C, limit of integration from minus infinity to plus infinity e to the power minus 2b x square dx. It's better to write the numeric number before these alphabets, it's better, but it's okay if we forgot to do that, just like me. Square e to the power minus 2b x square dx. Now it has been reduced to a form where we can just replace the values of these integrations. We can see that this integration and this integration is same, okay, and the value of this integration has been evaluated before when we were calculating the normalization constant, okay, so we'll simply insert their values right into these integrals. Before that we should know what their values are. Let me show you, people. So first is this integration, when we have e to the power minus maybe ax square, okay, let's say like that form, then this integration will be pi by a simply, and in our case we have e to the in power of limit of integration, limit of integration from minus infinity to plus infinity e to the power minus 2b x square, it's what we have, so we'll replace simply a by 2b, in place of a we will put 2b, so this is the expression, this is the value of this integration that we'll put right here, okay. We did the same while calculating the normalization constant. Now let's see what's the value of this integration, because it's same, you know, you can see both of these are same integrals, so we'll put the same value right into them. For this I'm introducing here the general form. The reason to introduce a general form is because the same integration will be integration rule will be used for the calculation of first excited state, and second excited state will have to use the higher form of these integrals. So that is why if I introduce people the general form, it will help you to apply it for all of the integrals that will come later for the other parts of this problem. So this for n in here, we'll see how it applies. So that is equals to pi by a, then we have this product 1 dot 3 dot 5 means all the odd numbers will be multiplied, but what is the last value to multiply? It's 2n minus 1. Okay, it depends upon the value of n how much odd numbers will be multiplied, will be self multiplied and divided by 2a to the whole power n. Okay, this is the general formula. You should remember it because it will help you to do various integrations that will come later. Okay, so the one we are interested in, we want to find out the value of this integral, right? So we can do our substitution to get its value, and it will work this way. Like we can see here that it's x to the power 2n. So what will make it equal to x square if n is equals to 1? If n is equals to 1, 2 ones are 2, so it's x square, just like the one we wanted. So this, if we want to find out the value of this integral, then we have to put n equals to 1 in this integration to get our value. Okay, so let us do that in rough work. Doing so, it will make it e to the power limit of integration minus infinity to plus infinity x square e to the power minus ax square dx. Now next, putting pi by a. Now here we need to put the value of n first. If we put n equals to 1 here, this is what we will get. 2 ones are 2, 2 minus 1, it means 2 minus 1 is 1. So we have to take the last digit to multiply as 1, which means the higher quantities will not be there. 2n minus 1 shows the last number in this sequence. Okay, and the last number in this sequence is 1, which is actually the first number as well. So only 1 will be there. Only 1 will be there. If it would have been 5, if with the value of 2n minus 1 would have been 5, it means that we have to multiply all the odd numbers till 5. Okay, 1 dot 3 dot 5, but it's 1, so it means we have to stop at 1, start at 1, end at 1, and it's divided by 2a to the power 1, which means 1 over 2a simply. And we have a is equals to 2b in our case, so let us do that as well. In place of a, you have to simply insert 2b. So 1 over 2 into 2b, pi over 2b, it's 1 over 4b. This is its value. Okay, only these simple modifications will give you your required result. Okay, so we need to insert this value and this value right into these integrations. Okay, let's do that. Here I'm writing starting from here, and I'll put the values of these integrals as I proceed with writing it. So 4b squared a squared c, then comes this integral, okay, x squared, and here it is. Here is the value of this integral. I'm just putting it right into this place. All right, now next is minus a square 2, I'm writing this 2 at first place, 2a square bc. Then we have this integral, its value is here, pi by under root, pi by 2b with whole under root. Then we have plus a squared m omega square by 2, and then this integral, and its value is this. I'm putting it right here. It's pi by 2b 1 over 4b. Okay, so let's simplify it, and it's 4b square a square c by 4b. I'm writing this 4b here. We'll cancel out the common terms, and here I just want to put the value of a square as well. We know that a was equals to under root 2b by pi, sorry, it was equals to a was equals to 2b by pi power 1 by 4, and we can see here it's a square everywhere, so let's calculate it here. So a squared will be equals to 2b by pi power 1 by 4 multiplied by 2. Okay, so it's 2b by pi whole power 1 by 2, which means under root 2b by pi. We can put the value of a square right here in each of these expressions, and it will be simplified a lot more. You will see how simple the term will become. So let's do this here. 4b squared by 4b we need to cancel it, but I'll do it at a time. So in place of a squared I'll wrote 2b by pi, and it's pi by 2b here minus 2bc, then value of a square, which is 2b by pi, and we have here pi by 2b already, then plus under root 2b by pi value of a squared, and then we have m omega squared by 4 2s are 8b, and we have here pi by 2b. Let's cancel everything. So it's 4b and 4 is cancelled, one of the b is cancelled, 2b here and here is cancelled, pi and pi is cancelled because they have both have under root. So we are left with bc here, small b and capital C. Will put the value of c just now, we'll put it since it's simplified enough, minus 2bc, these are cancelled out, these are cancelled out as well, plus then we have this and this cancel out, and we have m omega square over 8b, and it's bc and it's minus 2bc, so it will become minus bc plus m omega square by 8b. Since c was equals to minus h cut square by 2m, let's put right here it's minus b into c is minus h cut square over 2m plus m omega square over 8b equals minus minus becomes plus, so it's b h cut square over 2m plus m omega square by 8b. This is the energy expression so far, and here the b is the adjustment parameter for the unknown features of the wave function. Okay, next step is to use the variation equation. Okay, variation scheme, let's call it as equation number a. Okay, we'll use it later. We'll differentiate e with respect to b and we'll put it equals to 0. This is what the variational principle says, like putting the variation of e equal to 0, variation of e with respect to what, the parameters, will minimize it. So we'll minimize the energy with respect to these parameters and we'll set it equal to 0. That's how the minimization process works. So let's derivate this expression with respect to b and we'll put it equals to 0 and we'll find out the value of b afterwards. So let's do that. It's partial by partial b, value of e that we got is this, that is equals to 0. Now let's do that. h cut square by 2m is a constant, then partial by partial b will be applied on b. Okay, then we have m omega square by 8 as constant, so partial by partial b will be applied on 1 by b equal to 0. h cut square over 2m, this is equals to 1 plus m omega square by 8 1 by b. We know that b d by dx of 1 over x is equals to minus 1 over x square. Okay, derivative of 1 over x is minus 1 over x square, so similarly we'll write minus 1 over b square as the derivative of this expression equals to 0. Now what we'll do is, this is negative sign, so it becomes plus minus minus, so it's m omega square by 8b square equal to 0. Will, since it's being subtracted here, we'll take it to the other side of the equation, so it will become positive sign quantity onto the other side of the equation. Now we need b squared in one side of equation, so we'll take b squared here and all of these quantities here. So let's do that. B square here and m omega square by 8. 2m will be multiplied on the other side of equation and h cut square will be divided here. B square equals 2 ones are into 2 fours are 8, so it's m squared omega square by 4 h cut square, taking under root on both sides, so b is equals to m omega by 2 h cut. Okay, if we take under root on both sides, then we will get m omega by 2 h cut. It's like this situation, and we got m omega by 2 h cut as the value of this unknown parameter, which is b. Now we'll put this value of b into the expression for energy that we got, as well as the trial wave function that we had at first place. So for the energy we had, let me see what the expression was. Here it is, equation number A. So we had this situation. We'll put the value of b here to get the ground state energy. Let's put the value of b right into this expression of expectation value of ground state energy that we had in equation number A. So I'm just gonna put it in place of b. Okay, h cut square by 2m remains the same. Then we have b, which is m omega by 2 h cut, plus m by 2 8b as it is, sorry, m omega square by 8 as it is, then 1 over b. Here it's b, 1 over b will be equals to the inverse of this expression, which will become 2 h cut by m omega. Okay, so 1 over b will write, we'll put the value of 1 over b here later. H cut square by 2m m omega by 2 h cut plus m omega square by 8. 1 over b is 2 h cut by m omega. Let's cancel out the terms. So what we have is m cancels out. We have h cut square and it's h cut here. 1 h cut cancels out. We are left with h cut omega by 2 into 2 4, plus this m cancels out. This omega and one of the omega cancels out. It's omega h cut omega above this 2, and it's 2 fours are, so 2 fours are 8, so it's h cut omega by 4 h cut omega by 4, which will become 2 h cut omega by 4. Since both of them are same now, so it means 2 times h cut omega by 4. 2 ones are, 2 twos are, so it's h cut omega by 2, which is the ground state energy, and it is equal to the exact ground state energy for the harmonic oscillator in 1D. Okay, one-dimensional harmonic oscillator has exactly this ground state energy. So we can see here that the variational method, the approximation method, gave us the exact result when we use the appropriate trial wave function. So let's see what is the wave function for the ground state as well. And since we know the value of b and a as well, so we can determine the ground state wave function, which was a e to the power minus b x squared. Here b is the adjustable parameter that we got. A was equals to 2b by pi power 1 by 4. Okay, and b is equals to, what is b? It's m omega by 2h cut. Here in a it's b as well, so we'll put the value b here as well. So a is equals to 2 into b, 2 by pi into b. B is m omega by 2h cut whole power 1 by 4. So a is equals to 2 and 2 cancels out. We are left with m omega by pi h cut power 1 by 4. This is the value of a. Let's put it right into this expression to get the ground state energy. It's m omega by pi h cut power 1 by 4 e to the power minus, in place of b we will write, what we will write, m omega by 2h cut x squared. This is the ground state wave function, and it is equals to the true or exact ground state wave function of the one-dimensional harmonic oscillator. The variational method did its work for the 1D harmonic oscillator. This is the ground state wave function for the 1D harmonic oscillator, which is actually the exact ground state wave function for 1D harmonic oscillator. You can say that ground state wave function for 1D harmonic oscillator. The same statement could be said for the ground state energy that we got. Alright, so that is it for the ground state. Now let's do it for the first excited state. What I'm planning now is to upload a separate video for each of the energy calculation. Like there will be a separate video for the energy calculation or for first excited state using variational method, and similarly there will be another third video where I'll upload the derivation, the detailed step-by-step derivation for the energy calculation of the second excited state, because all of these calculations are really lengthy, and I'll link those parts in the description box so that you can easily reach them out. I'll also pin a comment where I'll upload the link, where I'll attach the links of those videos. After some time, I'll upload a single video where I'll compile all these 3 derivations in one video, which will be very lengthy video, but I'll upload it because sometimes students need it in one shot. So yeah, I'll do that as well. But I hope you got this method. I hope you got the derivation. I hope you got it. And like, share and subscribe. If you have any queries, you can ask me in comment section. Goodbye.